Hi, everyone. As Matt said, my name is Jesse Haber-Kacharski, and we're going to be talking today about Scylla and Kubernetes. And we have a nice punny title here. Scylla, our mascot at ScyllaDB, is an ancient Greek sea monster, and Kubernetes is actually a Greek word meaning a pilot or a helmsman. So we thought that these two things went together really nicely. I wanted to briefly talk about myself and the other presenter. I am a software developer with a pretty varied background in self-driving cars, embedded software, and distributed systems. And I really love both systems programming and applying math to solve engineering problems in interesting ways. My co-presenter, Moreno, is a solutions architect here at ScyllaDB. He's got a storied history in IT and a lot of experience as a solutions architect. And in his few months at ScyllaDB, he's already been doing a fantastic job, and it's been a pleasure to work with him. I wanted to talk very briefly about ScyllaDB, the company. We are a next-generation NoSQL database, which is functionally compatible with Apache Cassandra, except we have much better performance characteristics in terms of latency and throughput, and we're also fully open source, and we also have enterprise support. The history of the company is very interesting. Some of the founders have in the past created the KVM hypervisor, which powers much of the internet today. I wanted to start this talk really at the beginning, and I realize that this may be review for many of you, but for me, when I'm learning about a new system or a new solution, I really try to understand, and I think it's often helpful to understand the core motivation, the core problem, when you get right down to it, of why does the system exist and what is it doing? And to do that, first, I want to talk very briefly about containers and containerization. And again, this may be review for many of you, but when we talk about containers in the context of computing, we're referring to this idea of taking everything that an application needs to run, its shared libraries, its configuration, its dependencies, its operating system environment, like files on the file system, its networking interfaces, its resource requirements, all of that. And instead of managing those things one by one or in tangent with other applications, we package them all up into a self-described entity or a self-described unit that describes everything it needs to run. And we, instead of handling everything independently, we handle this thing like a big self-contained unit, like an atom. And we can deploy these units atomically. We can treat them like just a big thunk of stuff. And by doing this, there are several advantages. The first is that we can be more sure of the environment in which we're deploying our applications. We don't have to do as much work to set everything up. From an operating system point of view, it's also much more cheap to do this than to have several virtual machines, VMs, running in tangent. And furthermore, we can actually control, like with virtual machines, the exact characteristics of the application that's running. We can limit the network interfaces that are available. We can limit the amount of CPU time. We can limit the memory. We can expose certain parts of the file system or not. And from the application's point of view in the container, it's running in its own environment. It has full control of everything. So really, it's a unidirectional view that we're imposing on the application. And so this concept of containerization has been extremely popular in the last few years, especially through Docker, which is, I think, the dominant containerization engine and management system. But there are alternatives like Rocket, I believe, from CoreOS, which was recently acquired. And it's a very useful concept in computing. But once you start talking about containers and you start deploying your application into containers, or many containers, you run up into this problem of dealing with all these containers. Because even with a simple example that we might consider, like a web-based business, perhaps you have a storefront that you're managing, and you might have one application that is strictly concerned with deploying the front-end website that customers interact with. And you may have another application that handles payment processing for all the purchases that customers are making on your website. And you may have another application, which is the database that stores your inventory and all the past transactions. And this may also be a container. And so really, we have this problem of managing many containers, where they're running on physical hardware, how they're communicating, how they're being scaled, and how they're being deployed. And this is actually an extraordinarily difficult and varied problem. There's a ton of solutions that have been used in the past and in the present, but an extremely popular one right now, as you all may know, is Kubernetes. And Kubernetes is, as far as I know, the third generation of this kind of service. It was formerly an internal service at Google. It underwent a second iteration where they changed the scheduler. And now this third iteration is open source. And while it's still supported, I think, somewhat by Google, a lot of contribution comes from the open source community and other companies who are contributing their own resources to the project. So we talked about the fact that we have many containers and that Kubernetes is a system that helps us to manage all of these containers and deploy them. I want to talk very briefly about the nature of Kubernetes, just so we have a rough mental model in case you don't already have one. When we talk about Kubernetes, we're talking about a system that automatically manages the distributed state of many, many different computing resources. And these computing resources can vary in terms of the hardware they have and the CPU, the memory, the networking. They can vary in terms of their host operating system. We're describing hybrid environments. And what Kubernetes does is it maintains the state of our cluster in a distributed key value store. And then when we interact with the system, we send a request to the control plane, as they call it, which then communicates with all the physical hardware nodes in order to achieve what we want. And one key aspect of Kubernetes, its structure, is that it's declarative. So what we do is we describe through a specification, which Kubernetes calls a manifest, what we want to exist in our cluster. And Kubernetes has lots of different objects that can be declared and described. But we may say, for example, that we want our cluster to consist of 5 entities, and that we want each of these entities to have access to at least this much CPU time and memory. And then when we send that request to Kubernetes, Kubernetes will first examine the state of the cluster as it is now through this distributed key value store etcd. And then it'll look at what we're requesting, and it'll identify the difference between what exists and what we have. And then it'll use this notion that it has internally of controllers to sort of make a change to something in the cluster to get us closer to what we want, to minimize that difference. And eventually, after enough of these steps have progressed, the state of the cluster will match the state that we're requesting, and we're done. And the point being here that's really important is that we don't describe how to do something as operators of our Kubernetes clusters. We describe what we want, and the system figures out for us how to do that. So one example object, or one really key concept in Kubernetes, is a pod. And really a pod is just a process running in our cluster. And you can think about it as corresponding directly to a single container, like a single Docker container. Now, really, you can have many Docker containers on a pod that are co-located, but I think for simplicity's sake, we're going to think about a pod as being a single container running in our cluster. And the key point about a pod is that it's a logical process, which means that we really shouldn't think about the pod as being tied to a particular physical host of any over a duration of time. We can say that at 5 o'clock yesterday, the pod was running on this particular server for 5 seconds. But the key point of Kubernetes is that it knows what computing resources are available on all the nodes that are available to it in the cluster. The pod itself expresses what its resource needs are. And then the Kubernetes scheduler will, given the pod's resources and the rest of the stuff that's running in the cluster, figure out where to place that pod to optimize its execution. And so pods can be bound to different physical hardware. They can have different network addresses. They're really a logical concept, and it's ephemeral. It's moving around all the time. One other important concept that I want to discuss that's very specific to Kubernetes is a stateful set. And before we talk about what that is, I want to talk about the way Kubernetes deployments were often constructed in the past, which is we have this assumption of statelessness. So we may say that, for example, we have a container that describes a caching service that just caches requests to some server that takes a long time to fulfill requests. And these caches are totally stateless. They don't persist any data. We can have one of them or 10 of them. And we could say, we could automate the scaling of this resource so that if the load to a website increases at a certain point in time, we can automatically and dynamically scale up the number of instances of this pod. And, or alternatively, when the load goes down, we could scale the number of instances down. And this works great when your services are stateless. But when we start to talk about databases, in particular Scylla, we are not just stateless anymore. We have persistent data, which is the data that we're storing in our database. And we have to associate this data with a particular instance of Scylla. And furthermore, not only that, we also have to have a stable network identifier because unlike with other web services, a lot of the clients that we use to interact with Scylla are host aware, or they're intelligent drivers. They know that a particular partition may be on this host, and they know to communicate with that host. So a stateful set is a fairly recent addition to Kubernetes that allows us a couple key properties. One is that while pods may be running on different hardware at any given moment, we have stable identifiers for them. So for example, if we had 3 nodes, we'd have Scylla 0, Scylla 1, and Scylla 2. And we can always refer to pod 0 by this network name, and the cluster will always identify the correct physical host where the pod is running. The other thing that this stateful set does is it sort of allows us to specify a template for what kind of persistent storage each of these pods needs. And that means once we've done this, that storage will be associated with that pod over its entire lifetime, so we don't end up mixing and matching. This is quite useful. So I hope you have a rough idea of what Kubernetes is, why it's useful. I want to very briefly talk about some specific aspects of a setup that we've got for using Scylla with Kubernetes. We're going to expand this a little bit more concretely later on in the talk, but I just want to introduce these ideas now so that we can have a little bit of context later, and perhaps later as you're looking at the code, you can use this as a bit of a reference. So again, as I described, a stateful set allows us to associate with each pod a request to get some persistent storage. And these are called persistent volumes in Kubernetes. And we can specify not only the amount of space that we want, but also, depending on our cloud provider, the characteristics of the storage that we want, like solid-state disks or hard disk drives. And when the pod is created through a stateful set, it'll make this request. And the very nifty thing is that depending on your cloud provider, for example, Google Kubernetes Engine or Google Compute Engine will actually dynamically create these storage as the pods are created. We don't have to do this ahead of time based on what we anticipate the pods will need. It'll just say, if we spin up the number of pods that we have to 10, then the cloud provider, its integration with Kubernetes will automatically spin up the storage for us and associate it with these pods. And you can see that in the resources that we'll describe later. I suppose I mentioned this point already. I think the most important point here is that depending on the provisioner, the storage provisioning may happen a little bit differently. So the demonstrations that we've prepared today are all working with Google services. Similar integrations exist for AWS, but we're not covering those today. Another important point I want to bring up for this particular use of Kubernetes with Scylla is how we check for readiness. And so when Kubernetes deploys a pod on a physical host, and starts it up, the system is aware of when the container is running because the Docker container is running and it's reporting that it's ready and it's finished its thing, but we don't actually know when the service that's running on the container is ready. And so that is what we do is each pod defines for itself at the application level, when am I ready? When can I report to Kubernetes, to my cluster, that I'm ready to go? And like I said, this is an extensible sort of hook for the application to satisfy. The way we've done it here is we just have a very small shell script. And inside the shell script, we run node tool, and we just look at the status of our cluster. And if we see that the IP address of one of the nodes that node tool lists matches us, and that node is ready, then we say that we're ready to go. Furthermore, we have this lifecycle hook through Helm, which I'll describe in just a moment, which not only allows us to verify when a node is ready, but also allows us to run a hook to decommission a node when we're getting rid of an instance. And so we also use this mechanism to run node tool to decommission the node and distribute any data that it owns to the other nodes in the cluster. And so now not only do we have dynamic growth of the cluster, but we also have dynamic shrinking of the cluster. The final point I think I want to mention, and that's important, is how we seed the cluster. So Scylla does cluster management at the application level for itself. We have the gossip protocol to communicate cluster information. And so when a new node joins our cluster, it has to know who to talk to in order to join the cluster. And this is the function of the seed node. So whenever we have a Scylla installation, you'll often specify particular nodes to be your seeds. And if we were not using a stateful set, if we were using a static IP address, then things wouldn't work, because as we said before, the pod can be dynamically scheduled to an arbitrary node with its own IP address, its own network address. And so one of the advantages of the stateful set approach with these static network identifiers is that we can just specify Scylla 0 dot whatever the address is, and Scylla 1 and Scylla 2 as the seeds, and then those identifiers will persist and will always refer to the same seed nodes. So we don't have this problem of having jumping names all over the place. And what's interesting is this DNS property means that we don't have any custom code in Scylla to support Kubernetes. It just works. So what I'd like to do now is hand it off to our solutions architect, Moreno, to do a little bit of a concrete demo of some of the concepts I've talked about. He's also going to go a little bit into Helm, which is one method of putting all of these manifests into a sort of revision control and helping us to manage them also kind of atomically, also kind of in chunks. So now we can talk about an installation of Scylla like an entity instead of lots of different Kubernetes resources all working together.
Thank you, Jesse. So just a little disclaimer here. There are some pre-steps to what I'm about to show you here. So, for example, because we are using Google Cloud, you should have, gcloud command line installed, kubectl, and Helm. All those steps, they're in these instructions for the Helm chart. So when you go to our repository, you see the instructions there. But to save us some time, I'll go straight into the demo. Jesse, can you stop sharing so I can share my terminal?
Sure thing. You should be ready now, I think.
Thank you. Let me see. Okay. Can you see my screen, Jesse?
I can.
Awesome. So, as I said, I already have my Google Cloud installed, Google Cloud command line, kubectl, Helm, all installed here. And now I'm just going to run Helm install ScyllaDB and see what happens. Okay, so what it's doing here is all those pieces that Jesse just explained to you, they're being deployed in an ordered fashion, and everything is happening automatically. So we declared on the manifest files what do we want, and that's what's happening here. So let me show you a couple of things. Now that ran Helm install. Let me run Helm list. And it will show me what is the release name that Helm gave to this particular instance that I'm deploying right now. So for all purposes, from now on, our release is called intent order. So let me just put that on a environment variable just to make it easier on me a little bit. Cool. So let's see the status of our release. So you can see that we have that config map that Jesse told us about. The storage class is also here. We have a service. We have a stateful set, which we want, three replicas. And right now we have 2 pods, one completely deployed and the second one being deployed as we speak. We will have a third one in a few seconds. So let me show you, going back to what Jesse said, I would like to show you, because I see a question here on the question and answer about how Scylla know that the node is ready. So let's check this out. So what I'm doing is I'm running the node2 status command on the first pod, this one right here. So right now you can see by the output from node2 status that the first node, it's up and in normal state, which means it's operational. And the second one is on up, so it's up, it's working, but it's joining the cluster as we speak. So if you look again at the status, we'll see that all the pods are running. And if we look again at node2 status, we'll see that we have 2 nodes up and normal, and the third one is joining. Okay, one other thing that the Helm is going to give us, and let me show you again. When I run Helm list, in addition to the release name, it's giving it a revision number. This revision number is what we are going to reference when we are doing, we're changing the state of our release for any reason. So as an example, what I'm going to show you now is how to add 2 more nodes. So what I'm doing here on the Helm upgrade is setting the parameter replica count to 5. So you remember we saw before that the stateful set started with 3. So updating this number to 5. And let's see how it goes. Okay, you can see there's a 4th pod being deployed. And when you look at the stateful set, you can see that the desired number for this stateful set right now is 5, and we have 4 pods currently. Again, if we go back to node2 status, then we're talking directly to Scylla. Well, it's not joining yet, so we have to give it a little more seconds. Let me show you one more thing. I showed you before that we were on the revision 1 of the Helm chart. So right now we have 2 revisions. See? So it's after we changed after we declared, the new state that we want this stateful set to be in, Kubernetes in the background is working to get to that state. Let's see. Okay, so now we have 4 nodes already in Scylla and a 51 just joining. So we'll give it some time to finish. And then I want to show you. note that we could use Helm upgrade for any number of reasons. Adding another shard, let's say we have a different shard for a front-end application that is going to interact with Scylla. So I could use Helm upgrade to add this front-end and make it connect to Scylla. Or for any number of reasons, like, maybe I want to change a configuration, I want to add monitoring, all that stuff. So let's see. There we go. So now we have 5 nodes up and running. But let's say, I had this peak sales on Black Friday, and that's the reason I needed 5 nodes, but now I don't need them anymore. So again, I could use Helm upgrade, change my number of replicas to 4. And as I explained before, actually it was Jesse that did that. What it's doing right now is inside this 5th pod that's marked as terminating. It's running node 2 decommission. So it's streaming all of its data back to the cluster, so we don't lose any data. And and then it's going to kill the pod. Let's see status. Let's look at node 2 again. See, so now we're back to 4 nodes. And again, let's look at the revision history. Oops, history. And then we need the release. Cool. So now we have 3 revisions, right? And we have 4 pods. So another way to do what I just did would be to, do a rollback. So let's say that for some reason, when we did a Helm upgrade, we run into a problem, or we just want to restore the previous state. So all we have to do is to, type Helm rollback, the release name, and the number of the revision you want. So in this case, I will use revision 1 when we had 3 pods. And let's see if it does what. Yeah, cool. Let me show you Helm status again. You can see that the 4th pod is terminating. We can look at node 2 status, and the node should be leaving. Yeah, exactly. So it's up, and the L right here stands for leaving. So that's what's doing right now. It's streaming all the data back to the cluster, to the 3 nodes that we have right now, and then it's going to kill the pod. One more thing that I would like to show you guys is, because Jesse mentioned that before, but when you start a stateful set, in this case in particular, because we are using Google, Google Cloud is dynamically deploying a persistent volume. And we have the persistent volume claims, which are the manifest files that are going to ask for some storage for Scylla. And you can see that they are all here, even though we already eliminated 2 pods, which means that, one way or the other, even if you lose the pod, the data is still there, so you can do some stuff later and reclaim that data from the persistent volume claim. And to end this, all we have to do is Helm delete and the name of the release. And that is going to get rid of everything we did, except for the persistent volume claims. If you want to get rid of that, You either have to change the policy on your manifest files, or you can go and run a command for Google Cloud through the command line, or go to the console and get rid of them. Otherwise, it's going to stay there so you don't lose your data. Cool. Jesse, can we go back to the presentation?
Sure thing. One moment. Okay, the slide should be visible now.
Yes, it is. Thank you.
Great.
Okay, so now I want to talk a little bit about performance. As Jesse mentioned before, when you're using Kubernetes, for this particular deployment, we are using Docker. We are using our Scylla Docker instance. We did some work on benchmarking, a normal deployment versus a Docker deployment. And I want to show you a little bit of those results. This is going to be released as a blog post. It will have a lot more information. I just want to show you a little bit of it. So can you go to the next slide, please, Jesse? Cool. So every time we talk about containers, we talk about how easy it's to deploy and manage a container. But one of the trade-offs is that we are not as performatic as we would be in a bare metal or in a VM. So this is the first example I want to show you. This is, on the left side, this is the maximum throughput. We are using the same AWS instance on this benchmark. So on the left side, it's our AMI, so running on a VM. And on the right side, it's Docker on the same instance type. So you can see that, we lose a little bit of throughput there. Can you go to the next slide? And same thing with latencies. This is for 50% load or 50% max throughput. And you can see that we have the latencies for the 99, for the 95, and for average, all three histograms. And you can see that Docker is not as good as the AMI. And let me try to elaborate a little bit on why is that. Can you go to the next slide, please? So what I want to illustrate here is that the AMI performs better than the container, and some of the reasons for that. This is the screenshot of our Grafana monitoring. On the left side, you can see the load per shard, and on the right side, the request per shard. Each line color represents one shard. The top graph is for the AMI, and the bottom graph is for Docker. Because in a container, Scylla does not have access to the underlying OS and the hardware resources. In the AMI, we have complete control of the hardware. And by default, we can apply some optimizations like CPU pinning. So shards are never moved to a different CPU, and hence we can extract almost 100% efficiency. The same does not happen on the container. So on the bottom, these variations that you are seeing on the load per shard is because the underlying OS in the Kubernetes node, it's making those shards go to different CPUs. So we have context switches, and this is costly. So you can see that on the right side, you can see the impact on throughput. So you can see that we have more operations on the AMI and less operations on Docker. Okay. I think that's what I wanted to show you guys and to discuss. And at this point, I'll defer it back to Jesse.
Great. Thanks, Myrna. So I wanted to very briefly just recap what we have covered today in bulk. We started with a little bit of an overview about what containerization is and why it's popular. We talked about scaling resources. We talked about treating something like a big blob for ease of deployment and for managing hybrid hardware and computing environments. We talked a little bit about what Kubernetes is and sort of some basic mental models that we can use when we're thinking about how to interact with the system. And then we talked a little bit about some API objects in Kubernetes and some concepts of Kubernetes that help us to deploy Scylla on Kubernetes effectively. And then we had a demo of some of those concepts realized so that we could actually use Helm to deploy Kubernetes quite easily in a cloud environment. So we're very happy to take some questions now. We'll also follow up with all of these slides in a later recording as well in the future, which you should hear about. But we have some questions here that we can answer, so let's take a moment to do that. Let's see. I have a question here. The stateful set is responsible for creating DNS records for nodes, and the answer is yes. The stateful set feature of Kubernetes sets up an internal DNS server and creates appropriate records for all the instances that the stateful set consists of. So if you have a stateful set consisting of 4 nodes, of 4 instances, then records will be created for 0, 1, 2, 3, and those will all be updated if the pod is moved to different hardware. Moreno, do you want to take one?
Sure. What's the difference between Helm and the YAML manifest files? So Helm is kind of a packaging system for the Kubernetes manifest files. So when you go to our code and see our Helm chart, you see there that we have a manifest file for a service, a manifest file for a stateful set, we have a config map, and all that it's kind of wrapped up by Helm.
Okay, I'm going to answer one here. Will the Helm chart be available? So absolutely. We have a repository on GitHub called Scylla Code Examples, I believe, and it contains some examples of integrating Scylla with other popular applications. We had a previous version of this demo with manifest files, with individual YAML files, but we have a PR that's just about to be merged, I think, that includes all of this Helm setup that Moreno has demoed, and that should be available shortly.
Yes, and let me mention here to everyone that is watching us that this is the first version of the Helm chart. We have several things we want to incorporate there. We'll keep working on that and making it better for you. We want to integrate our monitoring and some other stuff there. And we appreciate if you can come to us even through Slack or even on GitHub and leave suggestions, tell us what we would like to see on our Helm chart.
Great. I have a question here. It's quite long, so I'm not going to bother reading it out loud, but the question is effectively, if with the stateful set system we have a node and the node goes down, or more correctly, maybe the instance goes down. Let's say we have 3 instances, 0, 1, 2, and one of them goes down, and we can make a new one. Is it going to be Scylla 4, or is it going to replace the one that was down? And my experience, and to the best of my knowledge, the answer is that it'll replace the downed instance, so that as much as the physical hardware allows, we will always have 3 instances available, 0, 1, 2, and that's why this stateful set feature is so nice. I hope that answers your question. If it doesn't, I can see it's a little bit in depth. Please don't hesitate to reach out to us in the community channels. Moreno, is there anyone that you'd like to take? I can try to take another one if you'd like.
No, there's some people asking about if it's recording. Yes, it's recording. You get the video later. The slides too. On the slides, we have the path to our GitHub repository, so no worries about it.
Great. And I have another question here about the recording. As we've said, it will be recorded. I see some questions here about specific setups that people are dealing with in their own company or their own machines. We're not going to answer those kinds of questions today. We would encourage you to use the community channels like the Scylla users Slack channel or the mailing list. And hopefully not only can we benefit from the solutions architects we have to the extent that they can, but also the rest of the community as well. And of course, I want to mention that we do offer enterprise support as well if your company is interested.
There's one question I would like to address here. So regarding the performance hit on Docker versus AMI, do you think there's an implementation issue that can be addressed with Docker Kubernetes? Yes. And one of the reasons we did the benchmark that I mentioned during my demo is that, yes, we learned some ways to get the performance back through CPU pinning, IRQ pinning, by properly benchmarking the disks. And if you need help with that, I encourage you, as Jesse said, to go through our community channels, go to Slack. You can ping me directly there, and we'll try to guide you through those steps. I didn't want to provide some documentation on it so far, because we are trying to automate that, and because doing it manually, we need to be very careful.
There's a question here, is multi-DC supported when Scylla is run in Kubernetes? And my answer at this point is I'm not sure. I'm wondering, Moreno, if this is something we have yet investigated.
No, I don't think we didn't test that yet, but all Scylla functionalities should be there. So it's just a matter of figuring out how to do it through Kubernetes. So I don't even understand. Well, for a multi-DC, what I think he means is we have some Kubernetes nodes in one location and another one in other location. And, well, theoretically, there's no problem in doing that. I think we can do it, but we didn't test yet.
Great, good stuff. Yeah, we'll follow up on this, or please feel free to ask on the community channels, as we said, and we can try to give you a more thorough answer. Maybe we want to take one or two more questions. What do you think? Oh, I see one here. Is there any contact information to learn more about Scylla and Kubernetes? So we do have the GitHub repository available. We're going to point to some resources after this slide here. In fact, I'd like to have these up now. Let me just switch to this slide. So as I said, we have this repository on GitHub, which will have the Helm specification available shortly. We also have a blog post that I wrote a little while ago, which describes an earlier version of this setup, and also, again, links back to that repository. And these are some resources that myself and Moreno have used in the past a little while to get up to speed ourselves on all of this technology and all these different concepts, and we think that they might be useful for you as well. Just regarding the Kubernetes documentation, I find it's extremely thorough, but sometimes it can be a little tough to navigate and make these mental models. So the best way, I think, to learn about these systems in depth is to read many different resources and try to build up your own understanding over time. So I think that's about good for questions that we can answer today. I don't know if there's something that jumps out for you, Moreno, but I think we're running out of time at the moment.
Yeah, one brief thing that I would like to mention. There's some people asking about configurations, and you can address that using the config maps that we told you before. So if all you have to do for some specific Scylla configuration is to create a config map for the corresponding Scylla conf file, and it will be there. Excellent. And again, if you need help, just come to us on Slack.
Yep, great. So as we said before, please don't hesitate to reach out. You can reach me at this address. I'm on Twitter, as many of you are as well. And Moreno can be reached at this address. We really encourage you to not only ask questions, but also to share with the community what your experiences have been. Maybe you have some tips or advice to improve these deployment strategies for Scylla, and those contributions are very welcome. Just a quick reminder, this recording will be available in the future. The slides will be independently available if you'd like to look at them. We have some extra information about the demo there that we didn't quite show you during this broadcast. And we look forward to seeing you at future webinars. Please stay in touch. Please tell us what you'd like to hear about. We're very happy to be working with all of you and to be getting better together. Thanks so much, everybody. I think that's it for today. And until next time.
Thanks, everyone.